Fine-tuning in Big Bang inflation. The fine-tuning dilemma in cosmic inflation theory. 30 to 50 physical parameters of the universe have been set to values that are very highly specified, within very precise ranges, to enable complex life to exist. This is prima facie proof for fine-tuning of the physical parameters of the universe for life to exist. And this, then, points to the existence and purposeful actions of a fine-tuner, i.e., God, who created and fine-tuned the universe to enable life to exist in it. To avoid this rational conclusion, some atheists have proposed, or appealed to, various hypotheses to avoid the evidence for fine-tuning. However, every single attempt fails to avoid the fine-tuning proof, beyond a reasonable doubt, for God. We discuss one such attempt in this video. Introduction. Cosmic inflation is a widely accepted theory in modern cosmology that proposes a period of extremely rapid expansion in the early universe, immediately following the Big Bang. This theory was introduced to solve several problems inherent in the standard Big Bang model, such as the horizon problem, the flatness problem, and the monopole problem. While cosmic inflation has become a cornerstone of contemporary cosmological models, it is not without its challenges. One of the most significant and often overlooked issues is that the theory itself requires a degree of fine-tuning of initial conditions to produce the universe we observe today. This video will explore the nature of this fine-tuning and its implications for the validity of cosmic inflation as a scientific theory. Understanding fine-tuning in cosmic inflation. Fine-tuning in cosmology refers to the idea that certain parameters or initial conditions must be set within a very narrow range to produce the observed properties of the universe. In the context of cosmic inflation, fine-tuning is required to ensure that the inflationary phase leads to a universe that is flat, homogeneous, and isotropic, with just the right amount of density fluctuations to allow for the formation of galaxies and other cosmic structures. The flatness problem in fine-tuning. One of the original motivations for the inflationary theory was to solve the flatness problem, which refers to the observation that the universe appears to be very close to geometrically flat, having a critical density. Without inflation, a flat universe is considered highly improbable because any slight deviation from flatness in the early universe would have been amplified over time, leading to either a rapid collapse, closed universe, or runaway expansion, open universe. Inflation solves this by rapidly expanding the universe, which stretches space-time to appear flat, much like how a balloon's surface appears flatter as it inflates. However, for inflation to work in this way, the initial conditions, specifically the energy density of the inflaton field, the hypothetical field driving inflation, must be finely tuned to a precise value. If the initial energy density were even slightly different, inflation might not occur, or it could produce a universe that looks drastically different from the one we observe. The horizon problem and initial conditions. The horizon problem is another issue that inflation aims to solve. It refers to the fact that regions of the universe that are now far apart appear to have the same temperature, even though they should not have had time to exchange information, light, and equilibrate. Inflation explains this by suggesting that these regions were once close together before being rapidly pushed apart. However, for inflation to solve the horizon problem, the universe's initial conditions must be such that the inflaton field is homogeneous across vast regions of space. This requirement implies that the initial conditions of the universe had to be set with extreme precision. If there were significant variations in the inflaton field's initial value across space, the inflationary process could not smooth out the temperature differences, and the horizon problem would persist. The issue of scalar field potential. The inflaton field is typically modeled with a potential energy function that determines how the field evolves over time. For inflation to occur in a way that produces a universe like ours, the shape of this potential must be finely tuned. Specifically, the potential must be nearly flat so that the inflaton field rolls slowly enough to sustain inflation for the necessary duration. This slow roll condition is crucial because if the potential is too steep, inflation would end too quickly, failing to produce the desired effects. Conversely, if the potential is too flat, inflation might never end, leading to a runaway scenario. The need to carefully adjust the parameters of the inflaton potential to achieve the right inflationary dynamics represents another aspect of fine-tuning in the theory. Quantum fluctuations and fine-tuning. During the inflationary phase, quantum fluctuations in the inflaton field are believed to be the seeds of the large-scale structure of the universe, such as galaxies and galaxy clusters. These fluctuations must have just the right amplitude, neither too large nor too small, to result in a universe that has the right amount of structure. If the amplitude of these fluctuations were different, the universe could either be too smooth, with no galaxies forming, or too clumpy, with the universe collapsing into black holes shortly after the Big Bang. The fact that the observed fluctuations match the required amplitude for structure formation suggests a delicate balance, again pointing to the fine-tuning of initial conditions. The inflaton field must have had a very specific set of initial parameters to produce the observed spectrum of fluctuations. The implications of fine-tuning. The necessity of fine-tuning in cosmic inflation raises important questions about the theory's naturalness and plausibility. In science, theories that require less fine-tuning are generally preferred because they are seen as more natural or likely to occur without special conditions. The fact that inflation requires such precise initial conditions challenges its status as a completely natural and self-sufficient explanation for the early universe's properties. The persistence of the fine-tuning in a variety of areas points to God as fine-tuner of the universe for life to exist. Conclusion 1. Cosmic inflation remains a powerful and influential theory in modern cosmology, providing solutions to several perplexing problems in the standard Big Bang model. However, the theory's reliance on fine-tuning of initial conditions faces significant concerns. The need for precise adjustments to the inflaton field's energy density, potential, and quantum fluctuations shows that inflation is not as natural as it might initially seem. This fine-tuning dilemma invites further exploration into the evidence that points to God as fine-tuner. 2. Cosmic inflation does not avoid a need for fine-tuning, which points to an intelligent fine-tuner, i.e., God. Summary: 30 to 50 physical parameters of the universe have been set to values that are very highly specified, within very precise ranges, to enable complex life to exist. This is prima facie proof for fine-tuning of the physical parameters of the universe for life to exist. And this, then, points to the existence and purposeful actions of a fine-tuner, i.e., God, who created and fine-tuned the universe to enable life to exist in it. To avoid this rational conclusion, some atheists have proposed, or appealed to, various hypotheses to avoid the evidence for fine-tuning. However, every single attempt fails to avoid the fine-tuning proof, beyond a reasonable doubt, for God. Thanks for watching. Please like, share, and subscribe, and comment below if you agree or would like to add your thoughts.